So I think we've been talking about quite a lot about redox potentials and then be able to predict the stability of various species in water. So continuing on that, we need to look a little bit look into the kinetics of this redox processes. So we're going to start working on what we call a non-complementary reaction. Redox reaction. What exactly is a non-complementary redox reaction? So let me explain this to you. Let's say if I have permanganate MnO4 minus, and then if it reacts with Cl minus, that's a chloride, to give you CO2 plus Mn2 plus. Let's say we have a redox process in which manganese in 7 plus state is reduced to 2 plus, and chlorine in a -1 oxidation state, which is chloride, is getting oxidized to chlorine. Now, if you really look at these two processes separately, what you find is the oxidation of chloride to chlorine involves the release of 2 electrons, 2 Cl minus giving Cl2 plus 2 electrons. All right. Now, if you look at the permanganate MnO4 minus to Mn2 plus, how many electrons are involved here? Can anyone guess? How many electrons are required to reduce the permanganate, which is MnO4 minus, to Mn2 plus? I mean, you all know how to do the redox reactions, right? So you have 4 oxygen, so you got to put 4 waters. That makes it 8H plus on the left-hand side, right? And then you have 7 positive charges there and 2 positive charges, so you need 5 electrons here. So permanganate to manganese 2 plus requires 5 electrons, while the oxidation of chlorine requires 2. So whenever you have dissimilar number of electrons in the oxidation half cell and the reduction half cell, if those 2 electrons are not equal, then we call that a non-complementary redox reaction. Okay. In general, non-complementary redox processes are kinetically very slow compared to a complementary process. So let me give you an example of a complementary redox process where the number of electrons involved in the oxidation and reduction half cells are identical. For example, if you take copper, 2 plus plus 2 electrons giving copper, and zinc, 2 plus, giving plus 2 electrons, giving zinc. So if I were to construct a galvanic cell based on copper and zinc, what I find is in both the reduction and the oxidation half cells, I have the same number of electrons. Whenever you have the same number of electrons in the reduction, the oxidation half cells, we call this complementary. So oftentimes, there will be reactions that will be given to you in an exam and ask you to identify which of the following are complementary, or sometimes they may ask you which of them are non-complementary. So the way you answer that question is write down the reduction half cells, oxidation half cells, find out how many electrons are involved in each of the half cells. If they are equal, they are complementary. If they are not, they are non-complementary. Now, if you really dig into the reasons why this happens, in general, what happens is if you take transition metals like D block metals, like manganese, titanium, vanadium, cobalt, nickel, copper, iron, in all those cases, the oxidation number generally increases by a unit of 1. On the other hand, if you take the P block nonmetals like nitrogens or chlorines, they require 2 electrons. So in other words, they are always in the steps of 2, while the d electrons always go in steps of 1. So anytime you mix d block metals with p block elements, and try to carry out a redox process there, you always get a non-complementary situation, generally, most likely. Okay, so this is a very important trait. So whenever you're looking at the redox processes, you have to be mindful of the unequal number of electrons that may be involved in the oxidation and reduction half cells. Is this clear to you folks? All right, so let me now continue with few other aspects of redox processes. Let's say if I have cobalt 3 plus ions in water. Question is, oftentimes we write in notebooks, yeah, we have taken a cobalt 3 salt and put it in water, but is cobalt 3 plus really stable in water? As chemists, we have to be very careful in writing this formula. So let me give you the relevant equilibrium for this. The cobalt 3 plus an electron giving cobalt 2 plus has a standard potential of plus 1.82 volts. Yeah, that is the oxidation potential. So it's a pretty strongly favored, thermodynamically favored process here, which implies cobalt 3 plus can be easily reduced. So cobalt 3 plus is an excellent oxidizing agent. So let's see if it can oxidize water. For example, the oxidation of water, the half cell of which is given as 4H plus O2 plus 4 electrons, has a potential of negative 1.23 volts. I'm writing this as an oxidation potential, right? Now, if you look at the overall process of this, the overall reaction is going to be 4 CO3 plus, 4 cobalt 3 plus ions, plus 2 H2O, giving 4 cobalt 2 plus O2 plus 4H plus. If you now look at this one, the cobalt is getting reduced and water is getting oxidized. So if you look at the standard reduction potentials, you can say this is the cathode minus the anode. So your cathodic potential is 1.82 and the anodic reduction potential is 1.23. So it comes to about 0.5 nanovolts. So what does that tell you about the stability of cobalt? Is it stable or is it unstable? The overall cell potential here is plus 0.59. What does that tell you about the spontaneity? Positive cell potential tells you it is spontaneous, right? I mean, I can keep talking, give the answers to you, but it'll be nice if some of you can look at this and understand and help me with the answers. In the exam, you'll be doing it yourself, right? So the point here we're trying to make is the reaction, the way it's written is spontaneous. So cobalt 3 plus is not going to be stable in water. So if somebody writes a cobalt 3 plus aqueous solution in water, you know that's not correct because cobalt 3 plus cannot survive in water. What is the stable oxidation state of cobalt in water is 2 plus. This is clear to you folks. Any questions? So the point then we have is what species are stable and what are not, and what are the windows here. So to give you an idea, I'm going to give you a graph here that more or less tells you how these things change. So for example, if you look at the reduction of water that is 2H2O, giving H2, 2H2 plus O2. That is the overall splitting of water there, in which water is reduced to oxygen, or reduced to hydrogen and oxidized to oxygen. So if you look at the oxidation potentials and reduction potentials, so the reduction here happens because 2H plus 2 electrons giving H2. That's the standard potential. We all know this is 0 because that's the standard hydrogen electrode. And for the oxidation of that water, 4H plus O2 plus 4 electrons giving H2O, that's going to be 2H2O. The potential for this is going to be plus 1.23 volts. Right? Now, all these half cells pH dependent. Do these potentials change when you change the pH? The answer is yes or no, folks. One of you.
Yes, it does.
Yes, Gurveer, go ahead.
I think it does.
It does. In fact, it does, because in both cases, I have H plus ions in the equation. So when you change the concentration of H plus, which is what you do by changing the pH, you're going to change those potentials, right? So if you were to look at the potential as a function of pH, so if you look at the formation of water potential, so at pH 0, that is your standard state potential, it's 1.23 volts. So what should happen to this potential when you increase the pH? Which way does it move? Does it move up or down?
Sorry, can you ask the question again?
The question is, when you change the pH for the formation of water from H plus O2 plus 4 electrons, what will happen to the potential 1.23? Is it going to increase, decrease, or remain the same? Am I clear here, folks? So what happens when you increase the pH? What happens to the concentration of H plus? Does it increase or decrease?
It will decrease. So it will decrease. So the pH will be lower.
When the pH increases, the H plus will be decreased, right? So the reaction will move backwards. When the reaction moves backwards, the potential is going to decrease. So as you increase the pH, that is going to decrease like this. All right. Now, if you look at the first reaction, H plus 2 electrons giving H2, the standard state potential is 0.0. What happens to this potential when you increase the pH? Does it increase, decrease, stay same? Again, we'll be thinking critically. That's the equilibrium we're talking about. 2H plus 2 electrons giving H2. I have H plus in the reactant side. So when I increase the pH, I reduce the concentration of H plus. So the reaction goes backwards. So the potential drops. So the standard state potential is good only at the pH 0, but any other pH, it's going to be smaller. Right? Now, we also talked a little bit about the over potential. The over potential, we said, is approximately 0.6 volts. So anytime if there are gases involved, we need to consider an excess potential that is required to release the gases. That's about 0.6 volts. So I'm going to add about 0.6 volts here. That is about 1.83 there, and go down in 0.6 volts here. So I'm going to draw again with over potential. So the solid lines here, what you see, are without the over potential, and the dotted lines here are with the over potential. So if the potential of any species, either here or there, that species is not going to be stable. So if you have a species up above here, it's going to oxidize the water. Or if you have the potential below 0.6 volts, negative 0.6 volts, it's going to reduce the water. So in either case, that species is not going to be stable. So the only species that are stable in water are those that have reduction potentials in the range of about 1.83 to negative 0.6. Only those can survive in water. All others will be destroyed by water, either by the oxidation of water or by the reduction of water. Either way, they're not going to be stable in water. That's what we're trying to say here. Is that clear to you? You see how beautiful this is? This graph will help you to figure out if something is going to be stable in water or not. If you look at the cobalt 3 plus, the example we did in the previous thing, that is above 1.8 volts. That's not going to be stable because it's going to oxidize the water. If the potential is less than 0.6, that's not going to be stable either. That's going to reduce the water. Like potassium, for example, has a reduction potential of negative 2.4, way below the negative 6 window that we are talking about here. For that reason, the potassium metal is not going to be stable in water. Am I clear here, folks? Any questions? Are we okay so far? Because we're going to slowly get into more advanced topics here. Some of this you may have known a little bit before, but I'm reviewing this for you. But what we're going to move on are some of the very important aspects of redox chemistry of inorganic metals and elements. Okay, so the next important topic that we're going to talk about today is what we call disproportionation. Disproportionation is a process in which a metal in a certain oxidation states undergoes both reduction and oxidation simultaneously. Let me give an example of a disproportionation process. Suppose if I have two copper plus ions, that is the monovalent copper, breaking down to copper metal and copper 2 plus. So what's happening here? We have two Cu plus ions. One of them is getting reduced to copper metal, and the other copper 1 plus is getting oxidized to copper 2 plus. Now, for a species to be stable, if copper 1 plus were to be stable in water, then this process in which the ion undergoes self-redox process, that is, it undergoes reduction as well as oxidation, that process should not be spontaneous. If it is, then that species is not going to survive in water. So to answer this question, we need to know what are the reduction potentials for the copper 1 and copper 2. So let me give you those values. So copper 1 plus an electron giving copper has a standard state potential of 0.52 volts. Okay. The next one, I have copper 2 plus an electron giving copper 1 plus has a redox potential of plus 0.16 volts. Using this information now, can we figure out if copper 1 disproportionates into copper and copper 2 plus, or it would not. How do we answer this question again? Here is our reaction. So to answer this question, we need to write the overall potential of the cathodic reduction potential minus the anodic reduction potential, right? Now in the cathodic production, I have copper 1 plus going to copper metal. That is the reduction half cell, that is the cathode, and the value for that is 0.52 minus the anodic redox potential is copper 1 plus getting oxidized to copper 2 plus, and the redox potential for that is 0.16. So that is 0.16 volts. So 0.52 minus 0.16. That is going to be about 0.36. What does that tell you about the spontaneity of this reaction here? When your potential is positive, the reaction is spontaneous the way it is written, right? Because the delta G for that will be negative, because delta G is negative NFE. So when the cell potential is positive, the free energy change is negative, so the reaction is spontaneous. So what does that tell you about the stability of copper 1 plus in solutions? It's absolutely not stable. Again, you have to keep in mind, these are all standard state potentials. So if you keep all the standard state potentials, that's all the concentrations of the ions at 1 molar, and the gas is at 1 atmosphere, temperature at 25 degrees Celsius. If you keep those conditions, there is no way in the world copper 1 is going to survive in water to give you any meaningful concentrations. So copper 1 plus will immediately break down to copper 2 plus and copper metal. So we say copper 1 plus undergoes spontaneous disproportionation. So if somebody writes a copper 1 plus aqueous solution in water, you must laugh at them, because copper 1 plus does not stay in water for a long time. It's going to break down. Am I clear here, folks? Let's take one more example to see if a species undergoes redox potentials. Let me give you another example. I'll keep talking if I don't hear from you, all right? Assuming that you understand this. So let me give you another example and see if it undergoes disproportionation. So here is an equation. 3 Fe2 plus giving 1 Fe plus 2 Fe3 plus aqueous. So solid. Watch this reaction carefully. I have 3 units of iron 2 plus ions in the solution. Should they disproportionate, then I get 1 mole equivalent of iron metal and 2 mole equivalents of iron 3 plus. Classic example of a disproportionation process. In other words, I'm trying to see if iron 2 plus is stable in water or not. Does it break down to iron and iron 3 plus, or does it retain its chemical identity as iron 2 plus? So the relevant information that I'm going to give you for this is iron 2 plus plus 2 electrons giving iron metal has a standard state potential of negative 0.41 volts. Okay. Similarly, I have iron 3 plus plus an electron giving iron 2 plus has a standard state potential of plus 0.77 volts. Using this information, can we predict the survival of iron 2 plus in water? Does it stay as iron 2 plus, or does it spontaneously break down to iron metal and iron 3 plus? I'll give you 1 minute to work it out using the same method that I have shown you for the previous example.
The cathode is going to be the one that forms the iron elemental, right? The element, the solid.
Yes. This is a solid, yes. That is aqueous. All ions are aqueous, okay? And we're assuming that the concentrations of these ions are 1 molar. Medina, you have an answer?
Not stable.
You think it's going to break down? So which part of the equation is stable? Is the right-hand side or the left-hand side?
Left-hand side.
Is stable?
I think so.
Okay.
So I
We don't
thought-
have to just calculate the numbers. So in one case, iron is getting reduced. Another case is getting oxidized. So that is the reduction. That's the oxidation. Simple, right? So we'll write down the cell potential, which is the cathodic minus the anodic potential. The cathodic potential is iron 2 plus 2 iron, that is negative 0.41 minus the anodic potential is 0.77. Right? That's going to be a big negative number. What is it? Negative 1.18 something?
Yes.
Yeah, that's it.
Negative 1.18, correct. What does that tell you? The potential is negative. The reaction is not spontaneous. So that now tells you that iron 2 plus is stable in water, unlike copper 1 plus. Copper 1 plus disproportionates spontaneously to copper metal, while iron 2 plus does not do that. Does it make sense? I'm going to go one step ahead and make another claim based on this observation. I'm going to claim that if you mix iron metal and iron 3 plus, if you are to mix iron metal and iron 3 plus, it's going to spontaneously form iron 2 plus. Am I making sense?
Would the sign just switch? Would it be like 1.18 volts, like would be positive?
If the forward reaction is not spontaneous, the reverse is spontaneous, right?
Yes.
So that's what I'm claiming. If you mix iron metal, iron powder, right? Metallic iron powder and iron 3 plus in solution, they will react instantaneously to form iron 2 plus. Because iron 2 plus is the most stable state between iron and iron 3 plus. That reverse process, the backward process, is oftentimes called comproportionation. You can see the board. The first one was disproportionation. So if disproportionation is not spontaneous, what is spontaneous is comproportionation. That is, an element in two different oxidation states combines to make one oxidation state stable. That's the reverse. Disproportionate is breaking down the same valence into two different valences. Comproportionate is a process just the opposite. Two different valences, like for example, here it is 0 and 3 plus, they combine to form 2 plus, which is more stable. Am I making sense here, folks? Does that make sense? Okay, let me give you some more examples to see how we can apply this in various situations. Let me give you one. I've written down some values here. As you all know, mercury exists like a dimer with two positive charges. So it is a case where each mercury is 1 plus state. Now that is proportionating into Hg plus Hg2 plus, which is solid, aqueous, and aqueous. So my question to you is mercury 1 plus stable in water or not? Sometimes the question may be that if I mix mercury with mercury 2 plus, would I spontaneously make Hg plus? Either way, I'm asking the same question. If it cannot disproportionate, then calm proportion is possible. So let me give you the values here. Hg2 plus an electron to give Hg2 2 plus has a potential of 0.911 volts. And Hg2 2 plus 2 electrons giving 2 Hg solid has a potential of 0.796 volts. So my question is this reaction spontaneous the way it is written? I'll give you 1 minute to do the calculation. Yeah?
It's not spontaneous.
It's not spontaneous because that is your cathode and that's your anode. That's where the reduction happens. This is where the oxidation. So if you look at the overall cell potential, the reduction part is basically Hg2 plus 2 electrons. I'm sorry, that should be Hg metal. 2 electrons. Yeah, that is Hg2 plus. So basically 0.911 volts. That is the cathodic process. That is Hg2 plus. That's the cathodic process, and then we have the other one 0.796, so it is 0.796 minus 0.911. I don't need to do the calculation. I know this is a negative value, so this is not going to be spontaneous process. So Hg2 plus will survive. In other words, if you mix mercury and mercury 2 plus, you will get a stable state of mercury 1 plus, because the disproportionation is not spontaneous. So one can envision thousands of oxidation states and looking at each oxidation state, which one is stable, which one is not stable, whether it can undergo disproportionation or comproportionation. So all these things can sometimes clutter. So in order to make life simple, we have a system called Latimer diagrams. Latimer diagrams are line drawings of various species. Let me give you some examples here. if you have copper 2 plus, going to copper 1 plus, going to copper. So we start with the highest oxidation state on the left-hand side, and then go to the next possible oxidation state, and finally to the final oxidation state of, in the case of copper, copper is a metal, so the lowest oxidation state you can have for a metal is 0, which is what we have. Now what we do basically on this is, we write 0.1519 volts. That is the reduction potential for copper 2 to copper 1 plus, and copper 1 plus to copper metal is 0.52. So this is a line drawing where all the oxidation states are written in the same line, and in the arrow that joins the two different oxidation states, on top of it, we write down the standard state potential for this. So this is plus 0.59 plus 0.52. Couple of things become very obvious when you write things like this. Here is the trick. If the right-hand side potential is greater than left-hand side potential for any species, that species is not stable. So we can say copper 1 plus is not stable against the disproportionation process. So just by looking at the line diagram, one can quickly say which species is stable. This is the simplest possible Latimer diagram one can think of. But if you look at any other species, I'm going to write down one of those. Let me say if I have perchlorate to chloride to chlorate to chloride to hypochlorite to chlorine to chloride. You see, all different oxidation states of chlorine here. Chlorine is 5 plus here, 7 plus here, 5 plus, 3 plus, 1 plus, 0, and 1 minus. Right? Now, if I write this potentials of each one of them on top, I get 0.374 here. That is the potential for ClO4 minus to ClO3 minus. ClO3 minus to ClO2 minus is 0.295. These are all available in the literature. You can Google them. And ClO2 minus to ClO is 0.68 volts. And ClO minus to Cl2 is 0.42 volts. And finally, Cl2 to Cl minus is 1.36 volts. Right? So these are all the oxidation states. Now, based on this, can you quickly tell me which species is not going to be stable against disproportionation? What did we say? Any species that has a right-hand side potential greater than the left-hand side potential is not going to be stable. So we need to examine ClO3 minus. If you look at ClO3 minus, the right-hand side potential is 0.29 and left-hand side is 0.37. What this tells you is this species is stable. Now, moving on to ClO2 minus, suddenly we find the right-hand side potential is 0.68 and the left-hand side is 0.29. That clearly tells you that that species, ClO2 minus, is not stable against disproportionation. In other words, if you have ClO2 minus, it will instantaneously break down to ClO minus and ClO3 minus. Right? Let's look at the stability of ClO minus. ClO minus is 0.42 on the right-hand side, 0.68 on the left-hand side, correct? So that species is going to survive, it's going to do fine. Similarly, Cl2 is 1.36 on the right-hand side, 0.42 on the left-hand side. So what does that tell you? Is Cl2 stable? if I put Cl2 in water, is it going to be stable? Does it stay like Cl2? That's my question. Since the right-hand side potential is larger than the left-hand side potential, the Cl2 will disproportionate in water to make hypochlorite and chloride. So Cl2, that's why will not stay in water as diatomic Cl2. Yes, Gurveer.
I was just gonna say, so if the right side is greater than the left side, means it's not stable, and so will not be stable in water as well, right?
That's correct.
Okay, I'm just making sure.
So if somebody gives you this table and asks you, identify the species that are not stable against disproportionation, then you know clearly ClO2 minus is not stable because the right-hand side potential is larger. Cl2 is not stable. That makes sense to you,
Yes, thank you.
right? Okay. Now, giving a line potential, we also sometimes will be asked to calculate what will be the potential from ClO4 minus to ClO minus, for example. Using this line diagram, can we calculate the potential for ClO4 minus to ClO minus? What will be the standard state potential? Any thoughts on this?
Do we have to identify which one is gonna be the cathode and which one is gonna be the anode?
No, but I'm already telling you, this is the redox potential, ClO4 minus to ClO minus, right? So if you want to write down the whole equation here, this will be ClO4 minus to giving ClO minus plus, there are 4 oxygens here, there's only 1 oxygen here, right? So we're mixing 3 oxygens, that will be 3 waters, and that makes it 6H plus, we have 6 positives and 1 negative. So you need to have about 6 electrons here, right, to make it overall this. So this is the reaction we're talking about, overall reaction. This is a shorthand version of it. The top one, ClO4 minus to ClO minus, is a shorthand version of the redox one. But what I wrote you in the last, that's the last line that you're seeing, is your actual redox process, which involves 6 electron transfer. How do we calculate this? Can we just add those numbers here up to this? Can we just keep adding 0.374 plus 0.295 plus 0.68 and give the answer there? Common sense tells us no, we can't do that because cell potentials is an intensive property of matter. So they are not additive. You can't add them. What you can add, however, are what we call the free energies or the enthalpies or the entropies. You can add them, but you cannot add the potentials. So how is this done then? So what we will do essentially is we recognize delta G is negative NFE. So if I know the number of electrons involved and the potential, so I can multiply the potential times the number of electrons times the Faraday's constant, that will be the free energy. So I have to convert each of the half cells into free energies and calculate the overall free energy. Once I know the overall free energy, I can then go back and calculate the potential using negative NFE because I know the total number of electrons involved. So here is a simple shorthand way of doing this. So whenever you are asked to calculate the potentials, the first thing that you need to do is, what are the oxidation states of the elements here? What's the oxidation state of chlorine here, folks? ClO4 minus. charge is ClO4 minus is minus
7
1, but the
plus?
oxidation.
7 plus, right?
You're absolutely correct, sir. Be confident. Yes. How about ClO3 minus?
It would be 5 plus.
5 plus. Very good. How about ClO2 minus?
3 plus.
Great. And ClO minus?
It would just be +1.
Plus 1. Great. Okay. So here is how I do this. Let me get my laser and then try to. Okay. What I will do is I'll multiply the number of electrons that are changed here. There are 2 electron change here, and those 2 electrons times the potential. So 2 times 0.374. That is proportional to free energy, right? The only thing we're not doing is multiplying by Faraday constant, because in the end, we're going to divide it by Faraday constant. So the only thing that matters is number of electrons changed plus times the potential. Similarly, from 5 to 3, I have 2 electron change with a potential of 0.295 volts. And finally, I have a 2 electron change with 0.68 volts. And that divided by the total number of electrons that are changed. This is 7, that is 1 plus, so there are 6 electrons changed. So when you do this calculation, can anyone tell me what that value is? We're going to, of course, practice a few more examples of this. So 2 times 0.374 plus 2 times 0.295 plus 2 times 0.68 divided by 6.
I got 0.45. 0.45.
0.405. Is it 0.4?
No, 0.45.
0.45 volts. I'm going to wait for somebody else to confirm this value.
Yeah, I got that.
You got that one. Great. That's 0.45. You see how simple it is. You cannot add those values, right? Because cell potentials are not additive. They're an intensive property of matter. So you have to keep that in mind. A lot of times students tend to think, I just add up these potentials from ClO4 minus to Cl minus and give that a value. No. Am I making simple here? We're going to do a couple more calculations. Let's say I don't want to go up to ClO4, but I want to go up to ClO3 minus to Cl minus. What would be the potential here then? That will be 2 times 0.295 plus 2 times 0.68 divided by 5 to 1 is 4 electrons. So can we do this calculation quickly?
I got 0.49.
and 4 nanovolts, right? Is that what everybody gets? We'll add one more. I want you to calculate the potential from ClO minus to Cl minus. This one is 0.49 volts, we know. What would be that potential? ClO minus to Cl minus. That will be 2 times 0.42 plus Cl2 to Cl minus, there's only 1 electron change. So 1 times 1.36 divided by 1 to Cl minus, that would be a 2 electron change. What would be that value, folks? We're
I
showing
got
all possible
1.05.
1.05. Is that what everybody gets? Just want to give one more minute to make sure that we all get this right. And you're all following my process, because the reason I'm giving you so many examples is to just to give you what is common here. We treat all problems the same way. Once we understand one, the rest is all simple. So is that what everybody gets? 1.405?
I got 1.1.
Somebody gets 1.1. Unfortunately, I don't have a calculator on me, but
I also got 1.1.
you got 1.1. So the 1.1 wins. All right. That's 1.1 volts. Now my question is this. The ClO minus to Cl minus is 1.1 volts, and ClO minus to ClO3 is 0.49 volts. So my question is, which species is stable? ClO3 minus, ClO minus, or Cl minus? Remember the rule, right-hand side potential, left-hand side potential, right? So we will now write it down very simply like this. ClO3 minus to OCl minus to Cl minus. This is 1.1 volt, and that's 0.49 volts. So what does that tell you about the stability of OCl minus?
It's not stable.
Is it really stable? It's very unstable against disproportionation. So we know OCl minus is not stable relative to a mixture of Cl minus and ClO3 minus. So the chances of you recognizing or measuring any OCl minus concentration in water is pretty small, because the hypochlorite anion breaks down to chloride and chlorate. Am I making sense here, folks? You see how we are building it up. We know how to calculate the potentials. And once I know the potentials for all possible oxidation states, I can then reconstruct different species and see which ones are relatively more stable. That's the power of Latimer diagrams. It's amazing. We'll take a couple more examples. Perchlorates, chlorates, we have manganese. write down. An acid solution, MnO4 minus to HMnO4 to H3MnO4 to MnO2 to Mn3 plus to Mn2 plus to Mn0. Right? So HMnO4, this is 7, and that should be electron there, that should be a 6 there. Minus 8, it should be a plus there, HMnO4 plus. HTMNO4, blah, 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 that's good. The potentials here are 0.56 volts for the first one, second one is 1.28, third one is 2.9, and MnO2 to Mn3 plus is 0.95, 3 plus to 2 plus is 1.51, and finally 2 plus to 0 is 1.18 volts. All right, so we have manganese in various oxidation states from 7 until 0, and we will have the potentials here. Now, the exercise here is which of these species is unstable with respect to disproportionation? Any questions, any thoughts on this? me
I'm
ask
not sure
you-
if I'm reading that right, but is it the Mn3 plus, the third one from the right? That'd be unstable, right?
You are absolutely correct, sir. That's a hotly debated topic. A lot of times, people don't understand this and they keep writing Mn3 plus in water. And that's a big no-no. So manganese 3 plus is not stable against disproportionation. In other words, manganese 3 plus will break down to 2 plus and 4 plus spontaneously. So we can say Mn3 plus will give you Mn2 plus plus Mn4 plus. This reaction is spontaneous. You may be able to stabilize Mn3 plus in solids, but in aqueous solutions, Mn3 plus unfortunately does not survive. What you instead have is 2 plus and 4 plus. On average, of course, it is 3 plus, but if you look at the individual species, you don't find a single manganese in a trivalent state in water. It's always a mixture of divalent and tetravalents. What other species do you
The
think?
third- The third one from the left, I can't read it, but I think it's H3MnO4.
H3MnO4, that's correct. Gurveer, that's correct. H3MnO4 is again another species where you have right-hand side potential 2.9 greater than the left-hand side potential 1.28. That's again a big no-no. So that doesn't exist. So what's the oxidation state of manganese here in H3MnO4? Is it 5 plus? No wonder you would have never seen manganese in pentavalent state in water. Because pentavalent manganese disproportionates into tetravalent manganese and hexavalent manganese. So you will never see manganese 5+. So when you combine all these observations and all the chemistry you have been learning over years and years, oftentimes you have been forced to memorize which states are stable, which are not. But we are at a stage where we don't have to memorize. We just look at the tables and figure out which ones are stable, which ones are not stable. Isn't it wonderful? And suppose if I ask you to calculate the potential from MnO2 to Mn2 plus, what would be that potential? You have to again understand MnO2 is 4+. So there's a 1 electron change from manganese 4 to manganese 3+, and a 1 electron change from 3 to 2. So it will be 1 times 0.95 plus 1 times 1.51 divided by the total number of electrons is 2 here. So that should, in principle, be approximately 1.23, right? Is that correct? I want you to check that number again one more time. Sounds close.
Yeah, that's what I got.
Great. So now we have those numbers. One more thing that sometimes people ask you is, which of these potentials, if any, will not be affected by pH? Which of those redox salts, like going from MnO4 to HMnO4, HMnO to H3MnO4, which of those will not be affected by pH?
Maybe going from I think it's HMnO4 to H2MnO4, or vice versa.
You have changes in protons, right?
Oh yeah, you do number.
So to answer this question, the way we want to do this is, we will write down the overall redox process. So for example, if I'm going from HMnO4 to H3MnO4, we will write that equation, balance it, and see what the balanced equation looks like. So HMnO4 to H3MnO4, right? So we clearly need to add 2 protons in the left-hand side, and then we have to add 2 electrons. Anytime you have a redox reaction in which you have free protons, that redox process is going to be affected by the pH changes. So clearly, HMnO4 to H3MnO4 potential is susceptible to pH changes. In fact, it's going to drop down when you increase the pH because you have protons on the left-hand side. In standard state, it is 1.28, but by the time you go to pH 9 or 10, it will be very small, maybe about 0.4. So now that you have an idea, can you now come back and tell me which of these potentials, if any, will not be affected by the changes in the pH? Any thoughts on this? already giving you a hint here. Whenever you have oxoanions, right? Oxoanions are, these are the MnO4s, MnO3s, MnO2s. Those would be affected by the pH changes. So you need to look for ions that are not oxoanions. That is, not oxygen containing anions. When you come to that, you have this portion of the Latimer diagram, right? Because if you have simple Mn2 plus 2 electrons giving Mn, has no proton influence. So whether you do this reaction in acid media or base, the potential remains the same. That's not true with HMnO4 to H3MnO4. That also explains why the pH changes in the solution sometimes affects the stabilities. So what is stable under pH 1 may not be stable once you go to pH 9 or 10, because the potentials are not going to be affected by those pH changes. So the Latimer diagrams give you a wonderful way of telling you which one is a strong oxidant, what medium you have to use. For example, I'll give you a simple thing on perchlorates. A lot of us know perchlorates are very strong oxidizing agents. So let me give you the perchlorate to ClO3 minus in acid medium, that is pH 0, is about 1.2 volts. Now, when you go to pH 14, the same Latimer diagram for the same conversion drops down to 0.374. So perchlorate to chloride in acid media is 1.2, but when you go to the base, 0.374. So if you have a chemist in charge of this oxidation process, in which of these pH is perchlorate a strong oxidizing agent? Is it an acid or in a base? Strong oxidizing agent means very high redox potential.
The acid.
Okay, what are these now? You are absolutely correct, sir. Because in acid, the potential is high. That means the reaction is more spontaneous. That is easy to be reduced. When a species is easily reduced, it's the strongest oxidizing agent. So ClO4 minus is a stronger oxidizing agent at low pH compared to high pH. So this is how scientists decide. I mean, one more word of caution, never try these reactions because perchlorates are pretty explosive. So never ever try to do these reactions. But the point here is a perchlorate behaves much better in an acid medium compared to a base. That makes sense to you? Any questions so far? So if not, in the next lecture, it's already, I can't believe the time is already up. We're going to start with Frost diagrams. And Tourbe diagrams, Frost-Emers diagrams. There are many, many ways of depicting these redox potentials. So we will work a little bit on the Frost diagrams. And after that, we'll get into the next topic. Frost diagrams will be the last topic for the redox chemistry. So we have covered quite a ground in terms of sterilities, in terms of Nernst equations, in terms of Latimers, disproportionations, non-complementary processes, stability of various oxoanions like perchlorates, chlorates, chlorides. So a lot of stuff that we have covered. So Frost diagrams, of course, we can teach this course for the entire semester, but we need to move on because there are other important aspects too. So in the next lecture, we will start with the Frost diagrams, try to give you an idea about how they look like, and then quickly jump into the chapter on catalysis, which is a very important topic, both heterogeneous and homogeneous catalysis. Then we'll touch the basics and give you some ideas about how this catalysis progresses. All right, folks. Again, thank you all for coming, and we will meet again Thursday, same time. In the meantime, have a great day. Bye.